Inviting me here today to talk. It's much appreciated, and I think MSSL, which is part of University College London, we've been in space work for many years, and we're also cost efficient. So I think our teaming with SSTL and SSC is a good teamwork for this project. I called it Shoot for the Moon, which actually is the article written by John Excel for the Engineer magazine. And there's been lots of publicity. It's been on BBC several times. We've had 30 or 40 magazine articles written about penetrators for the moon. So it's very good for public outreach. And we're teamed with very capable institutions in the UK, including Imperial College, which are supplying microseismometers, the Open University, geochemistry, Birkbeck, that's Ian Crawford, London, he's our chief lunar scientist. Kinetic are key in that they're from the defence, a defence contractor, but they've got lots of experience with hard impact devices, and University of Leicester newly joined us to do with X-ray fluorescence. Now I'm going to start off with a little video just to show you what the mission looks like. There's the SSTL satellite, and it's dropped a penetrator off as it's gone around the moon. So it looks like it's in the wrong direction. It's coming down. NASA were very interested in this video. They want to know all the details of how we got it, because we got it for free. I don't know how much NASA would pay to get a video like this produced, but it might be quite a lot of money. It's not quite the penetrator it's really going to look like. This is an artist's impression, and the attitude control system is not what SSTL would predict. It lands on the moon. Right, it's called Moonlight. Okay, so that's the general architecture for delivering a penetrator to the moon. Go back to the... just so you know what a penetrator looks like, I'll start with... It's not working very well. There's a real size one that should look very similar to one that's going to go to the moon. This is made out of aluminium. It's about 1/2 meter long. When it's full up with scientific instruments, it should weigh about 13 kilograms. It either has an aluminium nose or a steel nose, depending on what we think the hardness of the regolith is going to be after our studies. So penetrators, these are instrumented projectiles, and they've got to survive a high-speed impact. The kind of impacts we're looking at for the moon is going to be about 300 meters a second. I'll show you that a bit more later, and it should penetrate the surface, as Adam said, a few meters. These are an alternative to soft landers. Soft landers are generally more expensive. They've got to have very precise controls to get them to land appropriately. And at this kind of mass, they're much cheaper. And because they're low mass, you can deploy them widely across the planet, not just in one location, but several locations. And that allows you to produce a seismic network, because we'd have seismometers in there. General architecture of the penetrator, the bit I've got here would be the front end, which is the penetrator with the instruments inside. It would also have power system, communications, etc. The rear end is the other bit, would be the delivery system, and the whole thing together would be the descent module. The delivery system has got the propulsion, and it will be separated before it lands. There's quite a few challenges. It's not just the impact, survival of impact, which is a challenge, because if you hit something at 300 meters a second, that's quite a challenge. But there's also, you need to communicate from underneath the regolith back to your orbiter. There's a power, lifetime, and cold thermal issue. If you're underneath the regolith, you can't get solar power. So we're proposing batteries, and this mission's got to last for a year. If we land near the North Poles in the permanently shadowed craters where there might be water and other volatiles, the temperature there might be only 50 Kelvin, and we might need RHUs for that. It's very cold. We need to deliver this system. That would be SSTL's responsibility, but that's not an easy thing to do. And if we go beyond the Moon to Europa and the other planets, the radiation could be a big issue. And probably one of the biggest issues is funding. It's probably one of the most difficult things, and we spend a lot of time on. And that's one of the things that cause the launch things to go to the right, because if you don't get the funding, you keep moving to the right. So we don't have to just sort out survival of the impact, we've got to sort out all the other issues as well. Though we have done something to sort out the impact survival. This is a graph from a cannonball. I got interested in the history of cannonballs and things to do with speeds and things. I've actually got Mach numbers on here, which is interesting even in the time of cannonballs. And this is the drag against speed for a cannonball. We're not too interested in the drag at the moment. But if you fire a little revolver, I mean, that's about 1,000, that's 300 meters a second. The muzzle velocity, a fighter aircraft can go a lot faster, but commercial airliners, maybe the same velocity. And the penetrator to the Moon is going to be the same velocity as that. So we've got to survive hitting an object at nearly supersonic velocity, and sensitive instruments for science have got to survive that. History, as Adam said, there's not been a great history of success at the moment. There's never been a survivable high-velocity impacting probe ever landed on any solar system body. There's been a lot of paper studies, and the Japanese Lunar A mission was cancelled. It took them too long to get it developed, but they didn't have the defense contractor to work with them. But they now plan to fly on the Russian Lunar Glob mission, but it's very quiet in the press, so we don't know how that's coming on. Mars 96 was another penetrator mission, but it's much slower impacting velocity than what we're planning. That was just about 80 meters a second. And it wasn't a fault of the penetrators. It actually failed to leave Earth orbit. And the one that got the furthest was the NASA Deep Space 2 Mars mission, and that failed in 1999. The penetrators were deployed from the spacecraft, but never heard from again. Which doesn't sound too good, but on the other hand, the soft lander was deployed from the spacecraft and they never heard from that again either. So why people believe that penetrators are any worse than any other technology, I don't know. It doesn't really make logical sense. But are they feasible? The Lunar A and Deep Space 2, they built them, they space qualified them. So they believed they were feasible. And the military in this country, they've been successfully firing instrumented projectiles. I mean, this is what this looks like here. And I got some funny looks as I walked across the quadrangle, bringing it into the building. But they've been doing that for many years. They've spent hundreds of millions of pounds, maybe more on this, and they fire them into concrete and steel. I've seen videos where they go through 2 meters of concrete and survive. In fact, our expert in kinetic, we said, well, do they get a bit deformed when they go in? He said, oh, no, not deformed, but, they do get a bit scratched. And most of the scientific instruments we're going to put on here have got space heritage, but they don't have the ruggedization heritage, so they've not been proven to survive impact. But we've already done something about that, and I'll come on to that. The involvement of MSSL in this, we became interested in microprobes just after the start of this century. I can't believe it's really this century, but I know it is now. We initially started exploring an Aurora route into landed vehicles, because it seemed to me that ESA were not doing much in terms of landed. They're doing a lot of orbital stuff, but the future was in landed. And around about 2005, there's a new ESA program called Cosmic Visions, which is for missions to be launched 2015 to 25. And it seemed a long way away in 2005, but when you think you have to start building these things at least 6, maybe 10 years before, I felt that we needed to get it on the ground floor, so we needed to do work on it. Then in late 2006, PPARC initiated their Lunar Mission studies, the STFC studies, the STFC, involved in. We proposed penetrators to this. I remember a meeting with Yang and Alex Ellery at SSTL. We proposed this. And from that, as you've heard, Moonlight was selected for the first mission to the moon. And Mike Gribbin from NASA described the mission as inspirational. And whilst this has been happening, I've also been promoting penetrators for the icy planets, Europa, Titan, and Enceladus. It's quite interesting because I went to my boss one day and he said, well, I'm going to have to spend all my time on the moon. Can you concentrate on the other bits? And I remember being as a child, I used to be sort of jealous of people who were sort of area manager of Europe or East Pacific and that. And I was never manager of anything since then. But I thought, wow. I went out of his office and say, I'm now area manager for the outer solar system. That's good. But since then, since the Moonlight thing has come on board, and the cosmic vision, it's been like riding the back of a tiger. It's been getting faster and faster and more energetic, the program. In terms of the payload instruments, what you can get for a couple of kilograms, microseismometers, these allow you to study the inner body. I'll come on a bit more. You can get a mass spectrometer inside one of these. This is a compartment that would go inside one, and you can get a mass spectrometer inside that. Well, it's got to fit in that, because if they don't get it in, then they're not going to fly it. But they've got some really small ones. And the soil environment packages, the accelerometers, they're qualified to 100 kg. Normal spacecraft G-forces are like 40 G, 140 G. We're looking here for 10,000 G, 20,000 G. We're 2 orders of magnitude beyond anything that anybody else has considered doing in this country. And the accelerometers, they'll be able to measure how hard the material is you're going through, whether there's any layering. There's other thing like dielectric constant. That's useful for if you get an orbiting ground penetrating radar. They need to know the dielectric constant of the material to interpret their data. So it's useful to have an instrument that will do that. And we can also get radiation monitors, magnetometers. Adam was talking about them only for soft lenders, but we can get them in a penetrator that size. We can get all of them in a penetrator that size. There's another concept I've got for the outer planets, which is a mineralogy, astrobiology camera. You just have a little window in the side of the penetrator with maybe a quartz or something, and you have a little UV light that you shine it through, and it will fluoresce in UV. DNA fluoresces very well in UV. So if you get a little worm or something, you'll get not only the fluorescence, but you'll see the shape of the worm. If you do it again in an hour and it's moved, let's say if you didn't kill it when you actually landed on the moon first. But also, it's not just an astrobiology camera. You can look at the mineralogy of the material under the surface. And the other thing that's not been mentioned at the moment is a descent camera. So as you're going down, you want to take a picture of where you're going to land, so you've got geological context of where you hit. And that's all for 2 kilograms. So this is what we're aiming at. It's a very low mass. We need high technology, which is just what the UK wants, to develop high technology. Now I'm just going to go a bit about some of the prime targets, not just the moon. I'll come on to the moon, but the other targets, Europa, Enceladus, and Titan. For Europa, it's a moon of Jupiter. We're interested, and they believe it's got a subsurface ocean. There's evidence that it has. But has it got life in the ocean underneath? And one thing is, if we land penetrators on there, we'll be able to determine whether there is an ocean, how deep it is. Ground penetrating radar is unlikely to be able to penetrate far enough to determine whether there's an ocean or how deep it is. And initially, they were thinking of having a probe on Europa, maybe several hundred kilograms, that would melt its way down into the ocean, which is very high tech, very ambitious, and very heavy. For Europa, we'd go for a penetrator maybe half that mass, maybe 5 kilograms. If we can land it in one of these stripes on Europa, and you can look at the sulfur, and you can measure the isotopic ratio, you can determine whether there's life or not, because the isotopic ratios in sulfur very dependent on whether it's a geological origin or an astrobiological origin. So it's a closer picture.
All the way through.
Sorry?
Unless it goes all the way through.
What, the penetrator? Well, I think it's the surface of Europa, we don't know exactly, but it could be really hard ice. It might actually go in only maybe 20 centimetres, or if it's very soft material, it might go in tens of metres. But I don't think it's going to go not all the way through, not a planetary object. And here's a much more detailed view of Europa, kind of sort of fascinating images. So the key thing with the penetrator is if you can, you land in an area where life has come up to the surface. It's probably not going to be alive because there's very heavy radiation on Europa, maybe 5 megarads. Enceladus is a tiny little world around Saturn. You see here, compared with the UK, it's smaller than the UK. This emits oxygen compounds, so we think there's going to be water there under the surface. A penetrator could find that. Titan, I didn't know, but it's a fascinating body. All I knew is from Wikipedia a few years ago that it was just cloudy, very mysterious. But with Cassini-Huygens, they've now seen dunes, like on Namibia, so thousands of miles of dunes. There's fluvial plains that you've seen from the Huygens probe. We know that Titan has got a heavy atmosphere, maybe, it's not, even though it's just bigger, a little bit bigger than our moon, it's got an atmosphere 1.5 times as dense as Earth's. It's got mountains, dunes, lakes. It's got weather with winds, it's got clouds, precipitation, it's got seasons, complex organic chemistry, up to tholins. And it's very cold, you're right. Does it have prebiotic chemistry? Does it go that far? The current instruments can't go high enough. And does it have life? I mean, this is, to me, it's the most fascinating object in the solar system. But the moon is, if we go to the moon, it's got to be for world-class science, and it's not any way subservient to these other types of missions. So we're going to be looking at, as Adam said, the origin and evolution of planetary bodies, what it will tell us about that, about water, and what are the implications for that, and also to do with ground truth, because landers are not really in competition with orbiters. They're collaborative. They complement each other.